I'll just do a quick intro for you, and then I'll hand it over so you can do a screen share for your slides.
Okay, cool.
So look, so we have quite a treat today. Okay, so Eoin Mcloughlin, Principal Software Engineer at Microsoft, is joining us to talk about physics in glTF. He's going to give us a high-level overview. He's going to do some comparisons of how it's similar and different from what's in USD. And then, of course, we love the demos. This is super timely because Adam from NVIDIA, who's here today, also joined us last week to talk about USD physics. And I know that Eoin and Adam have even had some, some discussions and collaborations. And then I know, Eoin's been working on this and the team have been working on this for quite a while, but they just recently opened up the official pull requests in the glTF GitHub repo. So really excited for this today. A bit more on Eoin. He's worked on Havoc since 2007, especially on some of the hardcore multi-threading API design. Love his bio here. I'm just reading it, but keen interest in radio, open source software, tooling, visualization, and real-time applications, and dreams and bounding volume hierarchies. And from time to time, I do as well, Eoin. So very cool. Over to you.
It's more nightmares, I suppose. Okay, thank you. Thank you. Let me share my screen and hop right in. Can we see that? I hope so.
We can.
Okay, great. So I could literally talk about physics forever, but I've been given 20 minutes. So I'm going to try and make this as fast as possible. So what we're going to do is a quick whirlwind tour of a physics engine and recap for anyone that doesn't know. Then we'll just go into the details, the specifics of the glTF plus physics document. And we're going to then kind of compare with the USD and see there's a couple of differences, some big, some small, but we'll go into some of those details. So let's get started. Okay, no, let's not get started. Let's put some useful links in here. I'll put these on the end. This is my contact info. If you want to mail me with any feedback or any questions, more than welcome to it. Here's a link to the glTF physics pull request where into the Cronus repo. I've also been working on a Blender exporter, which generates that info so that I can actually test it. That Blender exporter probably has bugs, but I've been trying to squash them. And if you want to try running with it, also any feedback, more than welcome. And because we're going to talk about USD physics, there's a link to the USD physics documentation. So I'll pull those up at the end. And this slide is more for me. Physics is exceptionally broad. Again, talk about it forever. I'm going to take a lexical shortcut here. Anytime I say physics, what I really mean is rigid body dynamics. And rigid body is an object which doesn't change shape. So that means destruction and deformation, squishable objects, not really covered. People tend to use it, to use rigid body physics to generate like those kinds of simulation, but you tend to have to use tricks. And very importantly, physics simulation is not as embarrassingly parallel as graphics. You can't easily, some people do, run physics on your GPU. Physics tends to deal with pairwise interactions of objects, and you can have situations where you've got a huge complicated pile of bodies and there's lots of dependencies in between them and how they interact. So actually, one thing I should mention is most of our customers, not all of them, are games clients. So that kind of informs the use cases I think of daily. So I might have some biases there, but we try to be considerate of people doing serious simulations as well. So what a physics engine does is you have some world, it has some state, you have some real geometry in there, is teapots or glasses, cups and things, tables, and those have velocities. And what you do is you put those into your physics engine, you consider it a big black box, and it has this magic solver that resolves that state of the world, because one object will want to move one way, another object will want to move another way, and the physics simulation has to resolve that and turn it into something that actually happens in the real world. So the way you do that is you ask your simulation to advance time, and that will output a new set of transforms, new velocities for those bodies with unmodified geometry at that new position. And then next step around, you'll feed that into the same simulation. And the rigid body technology is pretty well researched at this stage. So what you could do is you can, you'll also generate events. You'll generate contact info. It'll say these objects started colliding with each other, these started overlapping, etc. We don't handle events in the spec, but we don't say anything about what they should do or say, but a physics engine will typically give you this, and you can use it to trigger sound events and things like that. So rigid body simulations have existed for a while. So most of the technology and the terminology is pretty well standardized. So you can swap out the Havok physics engine with NVIDIA PhysX, and the API will be slightly different, but the core concepts are going to be the same, at least to a first degree. Now, what will probably happen is you'll get a slightly different result, just because the physics simulations, they're doing a very complicated bit of work, and they're typically trying to run in real time, so they're taking a lot of approximations. And those approximations are going to be different. So no one's quite correct. No engine is more correct than the other necessarily, but you can get a different result from different engines. And even if you're not interested in objects that move, because physics typically deals with these simple bits of geometry, and it has very fast collision detection algorithms, you tend to get things like collision queries for free. So these things like build up an environment, build up some sense of the world. You can query a line from one point to another. You can get the closest point to an object, the closest point between two objects. And another slightly more exotic one is you can sweep one object from one place to another. So that you can say, okay, well, if I want to move my sofa from here to here, where does it hit a wall? Where does it hit a bit of geometry? Without having to actually do that calculation and apply a force on an object, you can just query the state of the world for that. And physics engines will typically, because they have these algorithms, they'll typically expose it. And again, we don't specify that anything, how these should be done in the spec, but it's kind of the advantages you get of using a physics simulation or using the algorithms employed by a physics simulation. And it lets you build up some sort of scene application, scene understanding, and kind of application specific knowledge or dynamic queries. So that's the end of the whirlwind tour of physics. That's what it does. So what are the glTF extensions? So this is the real meat of what I want to talk about. So there are two extensions proposed, and this was a split requested because some people suggested that the collision geometry itself, the idea that physics wants to work with a simplified representation of your geometry rather than your graphics meshes, just for performance reasons, people wanted to be able to use those collision primitives for other applications like UI in the future. So the collision geometry just provides basic geometric shapes, but it doesn't tell you what to do with them. It also has some filtering, which is useful for things, even if you're doing queries. But the guts of what it does is it gives you geometry that isn't necessarily triangles. Then the other extension is the MSFT rigid bodies extension, and that allows you to describe moving objects. And that builds upon the primitives that are exposed in collision geometry. So let's dig into collision primitives. All this is a set of primitives. These are they're listed in this table here: sphere, box, capsule, cylinder, convex collider, and a mesh. These are, you could come up with more sort of geometric primitives and mathematical descriptions of these primitives. These are the ones we typically see people use in games. They're both fast, and you can use them to approximate most of what you see in the real world quite easily. Sphere, box, capsule, and cylinder are probably ones that everyone's familiar with. Convex objects are basically the guts of what makes physics engines fast. Convex objects, there's really fast algorithms for colliding two convex objects together. And even if an object is not necessarily convex, you can, it's a reasonable approximation of objects that you typically interact with in the real world, or you can use convex objects to get compounded together to get a more accurate representation of your geometry. Convex objects also allow you to have a concept of being internal to a mesh, which is useful for kind of detecting penetration, which you don't necessarily get if you just have a thin triangulated tessellated mesh. And I just noticed this slide is out of date. We call this object a tri-mesh now. So for the next presentation, I'll update that. So what do those look like in your glTF file? At the top level of the document, we have an extensions object, we have the MSFT collision primitives, and that just has a big array of colliders, of all the colliders that are defined in the file. And I've just put one of each in here in 2 columns because it's quite lengthy, and they just have all the properties you expect. And it just says, what size is this object? Notably, the tri-mesh and convex objects, they reference a mesh object. That's the same mesh object that the nodes in the scene reference. So they reference the same type that your graphics object is, but they're not necessarily rendered. MSFT rigid bodies is the fun part of the proposal. This is the thing that actually allows stuff to move. So it's an extension object that you add to a node. It references a collider, which describes the collision geometry, which tells the physics simulation what that object looks like in terms of the collision, of how it should collide, rather. Then if we add a physics material to the object, that says this object should generate some sort of response. It should have a friction, it should have a restitution, it should push others out of the way. And then if you add a rigid body object to that extension, that provides mass, inertia, and velocity and allows the object to move. If you don't provide a rigid body, it's considered static, which is obviously doesn't occur in the real world. We don't have objects that don't move in the real world, but games applications will tend to use fixed objects all the time because it lets you make further simplifications and optimizations to your simulation. So what does this look like? So here we've got a node just in my glTF document. It has a graphics mesh, it has a name, it has a transform. And if I add the extension here, I provide a collider. I say it's index number 2 in the colliders array I showed you previously, and it's got a physics material 2 which indexes into a new object. Here we've added to the documents extensions, which provides some sort of physical collision response parameters. Then finally, if we add a rigid body parameter to that, we can give it a mass, we can let the physics simulation work out a mass if we want to. That says this object can move and will be pushed around. So body without materials. So if you create one of these nodes, don't specify a material. We've said this is a trigger object. This is useful for lots of scenarios, like detecting when a user or an object enters a volume. And lots of games will call these, or lots of game engines will call these triggers, phantoms, ghosts, all sorts of names. That name is unfortunately not standardized. But they're another one of those things that lets you build application logic. So digging into what the rigid body provides you, you've got mass, inertia, tensor, and center of mass, which describe the actual weight of the object and how it can move and how it responds to other objects and what forces that the solver wants to apply. Linear velocity and angular velocity are used to provide an initial velocity for those objects. It's useful to say my ceiling fan is starting spinning, or my airplane is starting flying. And then finally, the is kinematic object Boolean, useful for application critical objects that follow animations or follow some sort of procedural track, where you want them to move to a specific location, but you also want them to follow, push other objects out of the way. So people tend to use this for characters, elevators, that sort of thing in video games. And again, a collider without a rigid body is considered static. It's effectively infinite mass, and you can do tricks like static objects don't have to collide with each other. So the last object that we have that's interesting is a joint, sometimes called a constraint, and allows you to link two objects together. And mathematically, the solver that's used by the physics engine is the same. It's going to do the same thing for contacts as joints, but joints are kind of specified by artists rather than generated automatically by the collision detection. So that allows you to build door hinges, drawers, all sorts of fun things by limiting the movement of two bodies, or the relative movement of two bodies. So here's an example of some constraints. Let me jump into the middle of this. So we've got some sort of fake wind effect here and some constraint objects together, wind chiming, that you get lots and lots of these in video games or in simulations. They're a way of adding additional flavor to your simulation and hooking things up so they don't fall apart. So you can link, a joint can link two any arbitrary objects together, which kind of turns your physics scene into a graph, but the contacts are already doing that. And we specify pivots, so where the joint is on each body by adding child node to the body. So that allows you to have a transform that you can just point around and say, this is the axis I'm rotating around, or I'm allowed to translate on this axis and not allowed to translate on this axis. So we have a constraint object which tells you which axes to limit, if there's a min or a maximum on those objects, and if they're stopped by adding these spring constants, spring damping. I don't have an example of that, unfortunately. So that's the guts of what the glTF physics does. So in comparison with USD physics, the basic concepts are the same. You won't be surprised to hear, because the fundamental rigid body tech, not changing that frequently. So the feature set is almost identical, and most of the differences come from sort of the feature set of the two file formats. So in USD physics, you add a physics collision API to a node to make it collide, is equivalent to a static collider, and you add a physics rigid body API to allow it to move. And again, you can add mass properties, joints, filtering, etc., that all have a kind of equivalent concepts in this glTF physics spec. So the differences, so like I don't want to dwell too long on the similarities because that's boring. The interesting part is the differences. So USD physics has a particular joint, and it's equivalent to the glTF node that has a joint property. But USD has subclasses for some concrete types. So while the glTF physics spec has a very generic description of the constraints, USD also has specific ones for a ball and socket and a hinge or a prismatic constraint. They do the same thing mathematically. One is just a concrete representation rather than the abstract one. It also has drives or motors for the joints, so that you can constraints can push on themselves. I've been asked about this. We don't have that in the spec, but I probably will add that in the future as I've been asked about it. USD physics doesn't have a trigger object, but it's something I'd like to add soon. The USD physics group is currently working on deformables, so I don't want to rock that boat, but it's something I hope to get in the future. It also has an additional pairwise filtering object. So the filtering we use in the spec for glTF physics assigns categories to objects. But USD has something similar, analogous to that category, but it also has an additional pairwise where you can say this object should not collide with this one. That might be useful for some people. I'm not sure, but if anyone does want it, please let me know. And USD physics has a more complicated mass properties object. So while glTF physics lets you specify the mass and inertia and center of mass on the rigid body node. USD physics lets you assign mass properties to anywhere in the tree, and it has a set of rules for how those should be composed and how they should take priority over each other. And you can also specify an object density, which we don't have. So saying this object should have the density of water and letting the physics simulation derive what the actual specific mass is based on the volume. So that's not something we have, but I'm not opposed to mimicking the same set of rules. I think it would be useful to keep the rules consistent between the two. But I'm not, if people find it useful, I think we could do that. And last one, a comparison between what the actual files look like. So in this scene, we've got a box, a static box and a dynamic sphere. It looks like this in glTF. You've got nodes. I've got my cube, which is no longer a cube, but we've added the extension object. We've given a collider. It's collider 0, which is this box of this size, and it's got a physics material of this, which has friction restitution. And then the sphere again, mesh, name, transform, it's the same, very similar, just has an additional rigid body and a mass. Versus the same thing or very similar thing in USD. The world is akin to the scene. We have an object called a cube. It has a physics collision API to make it static. Notably, USD has built-in primitives, first class, baked into the file format. So the physics algorithm, the physics API doesn't have to specify that the size via a similar collision geometry extension. So yeah, same sets of properties, very simple scene, obviously, but they've added rigid body API, collision API to the sphere to make it dynamic. And this is just side by side, if you want to screenshot that and compare, but it's quite hard to look left and right, I'm going to be honest. And that's all I've got. I've got a little demo video I was experimenting with over the weekend, but I'll maybe open up to see if people have questions.
So I think we're good on time if you want to do the video and then questions.
Sure. Okay, so this is very much a work in progress. Just something I was experimenting with over the weekend. I took the Blender exporter I've got and Babylon.js, which is a web-based OpenGL TypeScript renderer, and just started adding support for the physics extension to it, and loaded up a scene, pulled up a bunch of random assets from our Perforce depot. So that's why you've got this weird mix of programmer art and things don't look right, but it was extremely easy to get stuff working. And then Babylon.js had this lovely just view. You can just go straight into Viewer. So I've added some basic forest application, and we're showing off some joints, lots of meshes, lots of colliders, stuff flying all over the place. I've been going through all these sorts of proof of concepts just to validate that the stuff we've described actually works and we can actually implement it. But it's far from production quality yet.
Cool. Well, look.
So that's all I've got, and I'm going to pull up the useful links again.
Cool. Well, first, thank you. I see the questions are coming in. So Guido, I think your hand was up first.
Yeah, no, just a quick question is maybe more of a reflection here. It would be interesting for both the groups doing this physics exploration, both on glTF and USD, to get together and explore what does it look like, a conversion, a lossless conversion. Because I think this is part of all this conversation is standards may diverge in some ways in some of the, but the best would be to be able to have a lossless conversion. So when we go from one to another, we have a mapping And if we don't have a mapping, there would be a worthy, I think, conversation with the two groups to understand if there is a alignment possible, or no, there is some fundamental reason why the mapping, because it wouldn't matter in a way if things are represented one way or another if there is a lossless conversation conversion.
Yeah. So I'm actually, I do participate in the USD physics working group as well. And I did try to make as much of the concepts match as possible. I think the USD physics is well designed. I think there's some good stuff in there. There's a couple of things that make it difficult. In particular, like the filtering. USD has a collection schema, so there's some things that we'd have to compromise on, I think. But yes, I agree that it should be as interoperable as possible.
Cool. And David, I saw you had your hand up too.
Yeah, real quick, this is a can of worms that we haven't figured out on the USD physics schema side yet. But even in the glTF, is there an understood set of units for all your quantities?
We have just specified mass, kilograms, seconds. It doesn't have the same, glTF doesn't have the same sort of units specified in the file that USD has. So there's a document, the glTF spec itself specifies meters and positive Y as the preferred kind of unit, for example.
But what about for like when you add motors and things like that, like and I guess, yeah, okay. So velocity will just be your meters per second, and because okay, so you're taking that route as well. So yeah, it's kind of similar in that regard. Okay. Real quick, I just want to circle back on Guido's comment. Guido, when you say lossless, I mean, we know from the outset that being able to replicate behavior in one simulator versus another, like that's just not possible unless we all agreed to all use the same simulator code and had that open source, as part of another standard.
I would say there's like renderers, right? We have different renderers, but if we try to, at least to the extent possible, to map the attribute and the intent, that would be already a good step. We understand that they will not be numerically identical at all, and it will not look at, but at least there is some, again, intent to be able to translate. And so then if we bring asset in one way or another, at least there is that. You're right. Obviously, they will not match the final result.
Or you could imagine saying, what if you round tripped an asset from glTF to USD to glTF, or the other way around? And then you were in the same simulator, would you pretty much get the same results?
Not necessarily, because so for example, the way we've designed the USD physics schema is we have a base schema that is the stuff that we believe should be common across simulators as much as possible. But then for a application specific simulator, let's say like PhysX, there's another API schema that can support physics only, like features only, right? But then maybe Havoc doesn't have those features. Maybe there isn't a one-to-one mapping. So there's sort of a base description that we, are assuming will translate, but then, everybody's simulator might have a different feature set. So
or maybe I can put it in a different way then. So obviously, yes, we expect the differences between the simulators. Ideally, there's each of these specifications is describing a physical reality in enough detail that you could pull out your classical dynamics and have enough information to specify analytically what those equations were going to be, and you get the same equations no matter which spec you would get, right? There's what is the physical situation, and then we have this numerical approximation to it that goes into every simulator. But I think the goal is, let's describe the same physical setup in either of these specs.
Right. So I think for that, Owen did a relatively a very good comparison about what the small differences are. And I think it's basically about those things that would need to be basically, we might need to add a couple things on the USD physics side, like the triggers that he mentioned. And then there is the number of things like, for example, joint drives on the glTF side that don't exist there. So it's a relatively short list of differences that would make the conversion lossy right now. Owen, one thing I didn't notice that I just remembered, kinematics, did I miss that? Do you have that in glTF, like basically animation driven objects that can push on physics?
Yeah, and it's the same bool it's the Boolean on the rigid body API.
Cool.
I wanted to, sorry, I have this horrible noise in the background. I don't know if you can still hear me, but I wanted to talk about the pairwise thing. I think that's valuable because you can have, you know, when you have a linkage or you have two pieces that are next to each other, you might need very detailed geometric relationships in order for them not to bump into each other. And you may choose not to do that in either the original geometry or in the collision geometry. And so you want to be able to specify that. And it's not really that they're members of a class, that this class doesn't interact with that class. It's really more of the idea that, hey, these things are really close. I don't want to have to specify their motion and their geometry so perfectly that they'll never intersect. So just don't worry about it. It's okay.
Yeah, one thing I didn't mention is that physics engines will typically have the option for a constraint, because constraints will typically overlap. You will want the geometry to overlap, but then the constraint will keep the objects from penetrating in an undesirable way. Think of like capsules for your upper and lower arm. They'll overlap at the ends. But especially when you consider the round tripping question, then I think having a pairwise filter then would make sense.
Another thing is kind of about semantics, right? And this touches on that exactly. Like, I'm not sure to what degree you have like a behavior spec with this. Like, it's exactly about this, right? So if you have a joint, for example, between two bodies, does that implicitly disable collision detection between the two bodies? You're saying right now that it does, but it would be good to like say these kind of things so it's unambiguous.
Oh, sorry, right? It's an option, and it's the same. I believe the same option exists in the USD spec, whether joint should enable or disable collisions.
Okay, cool.
Yeah, I guess the bits about the mass properties are not that disturbing, because when it's in USD, it's basically a lot of different ways that you can specify something, but in the end, you get an inertia tensor. And as long as that inertia tensor is the same one that you use on the other side, the details of whether you got that from a description of the parts that are set that have separate densities, or if you were given it directly, that's not really terribly fundamental.
Well, then is the concern on the round tripping about your intermediate representation, like the data at rest on disk after round tripping? Should it be equivalent, the same, or something that's equivalent?
I think if it's equivalent, that's good enough.
Yeah, I mean, we have small representation differences there. So, for example, I think in USD physics, we use quaternion orientation and then 3 principal moment scalars for the inertia, and then you guys are using a 3x3 matrix, which is not any arbitrary 3x3 matrix. It has to be I think it's like positive semi-definite or something like this, right? Sure. And therefore you need to convert, so you can't just like copy and paste numbers, both of them are fully able to represent inertia tensors of rigid bodies.
Yeah, I actually did a quick survey of unity represented principal axis rotation. So does, where do I find it in Unreal and USD or Omniverse, obviously also. No, I went off script. Sorry, it's in here somewhere.
It's not here. It's like you have to add a mass API because it's
oh yeah, yes, of course, yes, yeah. Neil, I see you hand up.
Yeah, I have a high level question just to understand the history and the context. Firstly, thank you for the great presentation, and it's great to see that the two specs are so close already. I'm just interested, the differences that remain, where did they come from? I mean, it's not a criticism in any way. I'm just trying to understand the flow and the path that we're on. Is it differences just because of different evolutionary paths of the two, and it's just inevitable that there are differences? We haven't tried to smush them together yet, or when you were doing the glTF proposals, were you considering different use cases or different target platform constraints or something like that? That informed different design decisions from the USD?
Yeah, so yeah, I don't think there's any particular reason we couldn't make them almost identical. But again, like some things like the way USD handles scene composition with layers, referencing other objects in different files, for example, you can do that with the USD pairwise filter, which you wouldn't be able to do in glTF. So there's some conceptual differences in the feature set of the file format itself.
Yep.
And there's some things that are probably like Adam said, the inertia tensor, that there's probably no particularly good reason. We just kind of chose one arbitrarily.
Yeah. Okay. Yeah. So of the differences that we have, then, what percentage comes from the kind of the intrinsic differences in approach between USD and glTF? Is that majority of them, or?
Yeah, like the mass properties, the collision filtering, probably the big ones.
Yeah. Okay. Cool.
I think, if the same exact people had worked on both, then it probably could have ended up closer, but it's actually really good that Eoin worked on both, because this way it is already really close.
Sure.
Let's put it that way.
Yeah. Cool. Thanks.
Do you want to say a couple more words about the different the joint specificity? I'm not sure I understood exactly what's going on there. So
yeah, so let me. I'm sorry I didn't include an image of the actual file. So when you specify a joint, what you want to do is specify the pivots in each object. So you have two objects. They might be aligned in the scene. They might not, depending on how they're authored. But in general, if you have one object, you want to say, this is my door frame. This is where the hinge is located on that door frame. And this is where the hinge is located on the actual door. And so that gives you a space in the space, that gives you a coordinate system in the space of each body. And within that coordinate system, you can say my x-axis, I want to limit movement on that axis. So if you wanted to represent a hinge, for example, when you physically link an object like this is a very abstract door. You'll say this cube, the position of the pivot on this cube should always match the position on the pivot of this cube. So what you want to do is you want to say that your linear axes, your linear x, y, and z should have 0 limits. And then what you want to say is your door is only able to rotate about this axis. So what you want to do is, exotic doors might have fancier linkages, but in general, you'll want to say that on the X and Y axis, for example, my angular limits are 0, and on the Z axis, I have a 90-degree angle free to move. So that allows you to build up a a bunch of limits within these two bodies. There's a couple of things you can't do with this approach. You can't make, rather, you can only do bilateral constraints which involve two bodies. You can't do pulleys, and you can't represent ratios between two objects where you say, if one thing translates, another thing should rotate, like a rack and pinion. So USD also doesn't have that. Someday I'd like to be able to support that in the file format, but I see rack and pinions and gears and things being used, pulleys being used extremely infrequently in at least our domain. And you can approximate.
I see. So basically, I think what you're saying is that by specifying these in various different ways, you can get the same effect as the collection of options that USD provides.
Yes. So the specific joint types, the USD also has the same sort of concepts for its generic joint, but it also has more specific concrete types for the joints, which are special cases of the generic joint.
Got it. Okay, so they're fully equivalent in the sense that you can represent, given one representation in one of the standards, you can create a fully equivalent representation in the other.
Yes.
The difference is, like, the fact that you have a special one in USD for hinge just means it's slightly easier for somebody to write it down, possibly.
Yeah, and I think that's probably the reason it's like that in USD. Maybe Adam would know.
Can you remind me, can I make a distance joint like this? Because I'm pretty sure you can use this to make the other joint types in USD physics. So you can make spherical, revolute, and prismatic. We do also have a distance joint, though, where it's like not clearly single degrees of freedom. It's like all positional degrees of freedom are kind of mixed, right?
Yeah, so the way you would do that is you can specify as many constraint objects as you like. So your distance joint would be a single constraint that limits all three axes.
Okay.
And has a min and max. And that gives you a spherical distance. Now you could do a circular distance, like an infinite cylinder, by specifying only two linear axes and a distance, for example. And then you could add a third constraint for the final axis to clamp the ends of that cylinder.
Okay, cool. Yeah, I think in that case, right. So we have like NVIDIA specific extensions, like for example, for rack and pinion, but I do believe that this really does cover all of the joint types currently in USD physics. With the exception of the drive capability. Yeah, there's also like this whole like articulation flag, like articulation root stuff that it's like important for robotics use cases, etc. But honestly, that's almost like an implementation detail. So yeah, honestly, it should not really be necessary if you have like a really good joint solver to need that.
Yes, ideally we would all have perfect physics solvers.
Exactly.
And what about the collision alternatives? I guess that's sort of solver specific right now in USD, is it? Or
the collision remember. What? Excuse me.
So they like the choice of using a convex decomposition.
Yeah, so there is actually one thing that David caught here is that we have in USD a cone primitive, and you did not add that to the geometry list here. But I honestly don't think that's a big deal, because I mean I really rarely see people use cones, and you do have a general convex object which lets you create a polygonal cone.
Well, so, yes, it just has flat faces.
Yeah. That's also a minor difference.
Yeah, one thing I didn't mention is the objects themselves, the actual the collider object has an extension property, so you can add more exotic. So someone that had a more exotic shape type, like a sign distance field or something like that, could specify an additional extension on top of this extension. Without
By the way,
changing the document
how do you specify a convex? Is it like polygonal faces? Is it some kind of support function? Like,
so we haven't described any particular data layout for the convex object. This object here, this mesh may be concave, and the spec says that you should derive the convex hull of that mesh.
So it's like,
so yeah, I know, like, it does mean you have to calculate it. You have to do that calculation, which could be costly. But I think it's better than ascribing a particular set of properties
that's the same by the way, that we use in USD physics. It's basically like a token hint to say that I want to, you know, collide this as a convex, but you put that onto a USD mesh that can also be non-convex, of course.
You might want to make it possible to promise that it's already convex, so you don't have to bother to compute the convex hull.
Okay, I'm thinking.
Even though a pedantic implementation would probably still check to make sure you're not lying, and then something, you know, nothing horrible goes wrong. Like, I would not trust you.
Right, but you know, if you want to make a faster implementation, you say, okay, yeah, I already checked, so you don't have to.
Yeah, well, one thing representations will do is our physics engines will do is they'll construct whatever whole representation is appropriate for them, and that might have polygonal faces. You can do collision detection with just the vertices, but some you might augment it with faces, face information, and connectivity, which the mesh may not have, the engine might want. So I'm thinking there's probably some calculation that has to be done anyway. One thing the PhysX extensions in USD and Omniverse do is they also store the PhysX binary blob of the calculated shape, which I think is really neat. And obviously that doesn't help if you're not using PhysX and not using the NVIDIA tools, but it's a really nice way of avoiding doing any calculations. Like in the same way, your tri-mesh objects for physics simulation, because of the queries you want to do, you probably want to build a bounding volume hierarchy for those. So there's additional calculations that are desirable for the physics engine to do if it wants to run fast.
Yeah, I agree with this, Owen. So I think the right level to do these kind of optimizations is not necessarily like in this kind of relatively high level USD format, but once you actually at one time ingest this stuff into your specific physics engine, then you cache out those objects so you don't have to do it again. One quick thing that I didn't see this, but maybe I just missed it. Do you have breakable joints?
I have not specified anything about breakable joints.
Okay, so USD physics has breakable joints with like a break force and a break torque attribute that you can.
Okay, we can do that.